Good morning. Let's begin with a quick summary of lecture 20 and move into the main topic of today's lecture, which will be the two-channel filter bank. Again, we will look at the complete development in context of the mathematical analysis, intuition as to what happens when aliasing occurs, where does the aliasing occur, and what are the forms in which the aliasing takes place, and then look at it. So, the review of yesterday's lecture, the key points that would like to mention. So, lecture 20 review, just two key points wanted to highlight. The first one is that we talked about the OFDM transmitter, and we have linked OFDM transmitter is in the context of an OFDM modem, the transmit section. We showed that this is identically equal in terms of functionality to a transmultiplexer, which does the conversion from time division multiplexing to frequency division multiplexing, and this is from a filter bank perspective. One point to mention, when we talk about TDM in the context of OFDM, TDM has got many channels. Each of them you can treat it as a narrowband channel. So, multiple narrowband channels. Typically in the time division multiplex system, these narrowband channels are interleaved in time. So, multiple narrowband channels. On the other hand, we have a single wideband signal. Okay, so, what you have done is you have taken a number of narrowband signals and place them in the frequency at different center frequencies. So, you get a single wideband signal, and this is a method that can be used to generate any wideband signal. So, that is one of the strengths of OFDM, that you can generate very wideband signals, 20 megahertz, 50 megahertz, 100 megahertz you can generate without significant increase in complexity, because what you are dealing with are primarily narrowband channels, which are then getting suitably multiplexed in the frequency domain. So, this is the key element from yesterday's lecture, and then we looked at the two-channel filter bank case and the result at which we stopped. Let me just pick it up from there. This is the M channel general setup, as we mentioned yesterday, different from a transmultiplexer. The conventional approach is that in a filter bank, typically the analysis filters come first, followed by synthesis filters. In a transmultiplexer, they are reversed in terms of position, because you have the synthesis happening first. But again, from our viewpoint, you can study it as a transmultiplexer or as a conventional filter bank, and we will take the filter bank the subband filter bank approach. So, the filter bank's primary job in the analysis section is to take a wideband signal and to split it into subband signals. Okay. So, we have taken the case of m equal to 2. We said that this is very widely used in speech and image processing. Using the two-channel filter bank, you can actually generate a tree structure. One of the key elements is why are we decimating by a factor of m? That was a question that was asked yesterday. Can we do greater than m? Can we do less than m? And so, the key points. Let me just sort of clarify that, just by way of it sort of also covers the review as well. Now, if you think of the sampling rate of x of n as some n samples per second, okay, and when you look at something that has been downsampled by a factor of m, this means this would be n over m samples per second, and you have m such channels. So, which means that the collective data rate of these still is retained at n. Okay. So, now if you did not do any downsampling at all, so if I do downsampling by a factor of m in each of the channels, then input rate, input, output. Okay, output would be the the collection of all the subband signals. If you have n samples per second, this is still n samples per second. So, basically you have not allowed any additional redundancy to creep into the system. Now, on the other hand, if we had taken the case of m equal to 1, so basically you did not do any downsampling. Okay, so, you downsample by m equal to 1. So, it is not the number of channels, basically I have just downsampling part alone has been set equal to 1. So, in which case if you have n samples per second, maybe this is not good notation, because m equal to 1 may think there is only one channel. So, basically you are downsampling by 1, okay, that means no downsampling at all. So, you will get n times m samples per second. The whole idea of doing dealing with subbands is to primarily for compression. Now, what have we done? If you do not downsample, you have actually expanded the signal. So, you are going in the wrong direction. So, the generation of subbands is really not beneficial at all. So, if you think of the primary motivation for splitting a signal into subbands, one could be for spectral analysis, but if you were also thinking of it in terms of compression, you would be very much interested in the case where you are. So, now can you go to less than n samples per second? Okay, that is a key question. Now, when it comes to compression, it is not only the number of samples per second, but the number of bits that you are using per. So, let us say that you are using B1 bits for each of the samples. So, it is B1 into n. If you end up with something which is B2 into n as your resultant, where B2 is less than B1, that is still compression. So, therefore, you have effectively done what you achieved what you. So, it is very important to note that one is you do not allow an increase in the sampling rate, that means number of samples per second, then you also reduce the resolution with which you represent it. So, compression can happen in each of those forms. Now, can I reduce it to less than n samples per second? Can I reduce it to less than n samples per second? If the original signal was sampled at Nyquist rate, that means you need n samples per second to represent the information. If you go anything lower than that, obviously there will be, because this is the net rate. So, you will run into the problems of representation. So, you will lose information. So, without losing information, if you want to represent, and if the original signal was Nyquist sampled, so since we do not know what the input signal is, we assume it is Nyquist sampled. So, then we say that okay, the best that I can do at the subband stage is to preserve the number of samples per second, not increase it, not decrease it, I may run into trouble, not increase it. And of course, then a compression can happen at this rate. So, why we are downsampling by a factor of m. Now, so when I have m channels combined with a downsampling by m, so with a plus sign, okay, m channels where each of them have got this operation, this is what we refer to as maximally decimated. Because anything greater than m will cause your greater than the number of channels where m is greater, will cause you to go below the sampling rate, the input sampling rate, which will cause problems. So, basically you are downsampling to the maximum extent possible, okay, that is point number 1. The second point is, once you have fixed your downsampling by a factor of m, what can you tell me about the spectrum of the signals going into the downsampler? It has to be around 2 pi over m, because if it is much larger than 2 pi over m, you are going to have significant problems with aliasing. So, that is also constrained. So, your subband signals, the bandwidth should be of the order of 2 pi over m. That again is sort of linked to it. Of course, you do have applications where you do non-uniform downsampling, and you can one of those applications, if you want to think about it, you visualize it, is in the following manner. Okay, so supposing I do a I do a 2-channel split. Okay, so I won't write down all the filters. There is a filter here, and there is a downsampling by a factor of 2, downsampling by a factor of 2. Okay, now I split only this branch as one more stage, downsampling by a factor of 2, and this is downsampled by a factor of 2. So now if you look at it, it looks like you have different sampling, downsampling in the different branches, okay, because you have 4 in the upper 2 branches and 2 in the lower branch. Now it looks like you have a non-uniform system because the bandwidth of these signals are different, but it has been constructed in a very careful manner such that each of these upper branches have got spectrum approximately pi by 4. This 2 pi by 4 is the bandwidth. This one will have approximately pi as the pi by 2 as the bandwidth. So again, the non-uniform nature can come because you are having more number of subbands on in one dimension. But the key point to note is that when I am doing downsampling, I want to keep the bandwidth of the order of 2 pi over m, the total bandwidth, so that we can downsample it and then preserve the and because these are practical filters, if I insist that both of them are let us say downsampled by a factor of 2, I do not want aliasing at all, then this will what will become the next filter. What will happen, that will also require no aliasing. So therefore this will what it that second filter will be. Now the problem will arise is that I do not know what happens in this information, signal is lost, right. So if I insist that my filters be such that there is no aliasing, then I will lose signal, information is lost. Now this is not acceptable because I cannot reconstruct. So the only practical approach that we will encounter is that these signals, this will be slightly wider than pi by 2 to capture all the signals, and this one will also be wider than pi by 2. So this overlap is inevitable. So there is going to be some amount of aliasing. So we kind of go into this subband analysis with the following aspects in mind. I want to downsample by the maximum downsampling rate possible, which is m. Given practical filters, then each of these must have approximately bandwidth 2 pi over m, which means that there will be overlap between adjacent sub channels, subband signals, which is fine, which may result in aliasing, but that is where the challenge lies, and that is what we are going to be looking at in today's class. So that is a sort of a quick review of where we are. So the 2-channel case, this input signal x of n, which we split into a low pass and a high pass signal, we call that as x0 and x1, and downsampled each of them, called it v0, v1. Then there is processing, but we said that in the analysis stage we are saying that we are not considering the processing. It is basically those signals are connected to the synthesis filters, upsampling by a factor of 2, filtering through f0 and f1 to preserve that portion of the, because upsampling will produce two copies of the spectrum, preserve that portion of the spectrum that you want, and then produce the output signal. So this was the setup. We went through the a few steps, basically simple steps of downsampling, upsampling and filtering, and we said that the input output relationship is given in terms of a transfer function t of z times x of z, that is the input signal, and a second term which depends on x of minus z, that is a frequency shifted version of x, that is where the aliasing terms come in. If that is present at the output, then there will be a distortion, because I will have input output depending on x of z the input as well as x of minus z, which is a shifted version. So we need to be careful with that. So this is pretty much where we stopped. We said that we could write this as a matrix equation which has the following structure. Okay, now I just wanted to quickly just sort of refresh ourselves that if you talk about h naught of z and H naught of minus z, okay, H naught of minus z. This is, if you look at it at z equal to E of j omega on the unit circle, this becomes H naught minus E of j omega. This can also be written as E of j omega minus pi, okay. E power j, write as E power j pi plus omega minus omega, does not matter, E power j omega minus pi. Okay. So, the reason we like omega is that it means it shifted, the spectrum got shifted from center frequency of 0, whatever the center frequency of 0 now shows up at pi. So, if you were to look at a signal or a filter of this type, this is H naught E of j omega, and this is what this would be the spectrum, this is 2 pi, this is 0. Now, H naught E of j omega will be located at pi. Okay. So, basically it is if the H naught is a low pass filter, H naught of minus z will be a high pass filter. Now, will the two of these filters overlap depends on the bandwidth of the signal. So, if you had chosen your original filter to have bandwidth which is beyond pi, let us say you chose 2 pi by 3. So, this is pi by 3 and this is pi. So, which means that the filters will have significant amount of overlap. So, I suppose that is something like that. So, when you shift it you will have, so the notion is that yes, we understand what H naught of minus z is. Now, at the input, I mean right at the subband splitting stage, we said that there is a constraint on H naught and H1, that between the two of them they must capture all of the information content in the signal. So, if you happen to choose H naught as a narrow filter, okay, and let us say this is pi by 2, pi, 3 pi by 2, 2 pi. Okay. So, basically you will get a copy of these of this filter there. Now, in order for you to actually construct the subband signal, this filter has to be of this type, right. It has to overlap, it has to pick up all of the remaining spectrum. Okay. So, when I downsample this red signal by a factor of 2, I am going to run into severe amounts of aliasing, because this is a much wider than pi by 2 and therefore, there is a penalty that I will have to pay. But right now all we are saying is between H naught and H1 they must capture all of the information, that is all the point that is being made. So, the key points to summarize are, we typically want H naught of z to be a low pass filter. Then H naught of minus z, which appears in our equation, is a high pass filter. This is H naught of z shifted by pi, the frequency response is shifted by pi. Okay. So, that is observation that we have made, and we now are interested in doing the aliasing cancellation. So, the aliasing term, if you go back and look at the last equation that we wrote, the aliasing term consists of H naught of minus z f naught of z plus H1 of minus z f1 of z. Okay, you can have a half or not, does not matter, maybe just put a half also there. This whole thing, if we call that as a of z, just some transfer function times x of minus z. This is the contribution of x of minus z to the output. So, basically this is what will show up at the output of x hat of z. This is not a transformation, this is what shows up, this is the contribution. There is a t plus, maybe to write it down, plus t of z times x of z, then you actually have an equal to sign. Okay. So, this is this is equal to, but we are focusing on the aliasing cancellation part. And over a period of time, very clever, intuitive, people with insight came up with several ways of dealing with this problem of cancelling the aliasing. So, the first or the earliest the solution that had come up in terms of cancelling the aliasing, I am going to call it as option 1, because there are several solutions that have come, and again I am sure that as you study this problem you will see that okay, yeah, this is probably a very obvious thing once you look at it carefully. So, the first one had the following solution. The choice was choose f naught of z to be equal to h1 of minus z, okay, and f1 of z to be equal to minus h naught of minus z. Okay. So, using these two combinations, would like to now verify that a of z is equal to h naught of minus z, f naught is h1 of minus z, you have a plus sign, you get h1 of minus z, and f1 of z is minus 1 times h naught of minus z. Basically these two terms cancel, giving you equal to 0. Okay. Now, what did this choice of filters actually impose? Did it impose any awkward or unintuitive conditions? So, here is a quick summary. If h naught of z is a low pass filter, h1 of z is has to be a high pass filter. Okay. Now, if you have split the upper branch as the low frequency components and the lower branch as the high frequency components, on the synthesis side, what should your filter f naught be picking out? It should pick out the low frequencies, right. That it would make sense, because the upper branch contains the low frequencies components. So, when you want to reconstruct the signal, you make the upper branch contribute the low frequency portion of the signal, the lower branch contribute. So, which means that f naught has to be a low pass filter, because when I do upsampling by a factor of 2, I will get multiple copies f naught. Now, does that satisfy? If h1 of z is a high pass filter, h1 of minus z will be a low pass filter. So, no problem at all. So, f naught of z will be a low pass filter. It is not connected to h naught, it is connected to h1, that's, and f1 of z automatically turns out to be a high pass filter, and it is connected to h naught of z. Basically it takes the low pass filter, shifts it, and also adds a phase. Basically minus is a phase term of pi, basically introduces so that those two terms can cancel each other. So, this is also another very key element. How do you cancel two signals? You make sure that they have the same magnitude response and then introduce a phase of pi, they will cancel each other. Okay. So, when you say that they have the same magnitude response, very important, this is a if you say that the spectrum of a signal is here and I want to cancel it, I cannot cancel it with a signal whose spectrum is elsewhere. I can only cancel when they are similar. So, I cannot cancel these two. On the other hand, I can cancel these two if I ensure that their magnitudes are the same and they have a phase. So, basically between these two, if they have same magnitude response and a phase offset of pi, then I can actually cancel the two spectra. Again, very key insight that happened. So, that is what was achieved in this process. You ensured that the transfer functions were the same and they had a phase shift of pi, and that is exactly how the so the key point is that using this option we can cancel aliasing. So, aliasing is now something that we have already handled. Now, what about the rest of the system? So, here is the remaining portion of the transfer function. So, the signal term, the aliasing term has vanished. So, T of z now comes out to be 1/2 of h naught of z f naught of z plus h1 of z f1 of z. Okay. Now, if you substitute the expressions, then we get this to come out to be 1/2 of h naught of z h1 of minus z minus h1 of z and h naught of minus z. Okay. Some very interesting symmetries are emerging, something for you to think about, and particularly all the concepts from signal processing now sort of come into play, basic DSP. However, we are going to take a very general approach where we say that okay, good that we got T of z. If I try to look at it in the frequency response on the unit circle, I can write it as magnitude of T e of j omega times a phase term. Okay. So, this is nothing but the magnitude response, or what we would refer to as the magnitude response of the transfer function. I can talk about a transfer function because it is now an LTI system, because aliasing has been removed. So, I have a T, so the relationship is that x hat of z is equal to T of z times x of z. So, basically the transfer function is T of z, I am relating it, and phi of omega is referred to as the phase response of the transfer function. So, we have the magnitude response and we have the phase response. Okay. Now, comes a couple of very key observations, very simple but very important. The first one says, if my T e of j omega, if the magnitude response is equal to c, a constant, okay, for all values of omega, then I do not have any magnitude distortion in my reconstructed signal, because it will be x hat of z, T of magnitude T of z, you can set it equal to constant times. So, basically this means that there is no amplitude distortion in the reconstructed signal, a very important one. Aliasing has been removed. Now, there is a transfer function. The transfer function says that there is a magnitude part and a phase part. Now, if there is something funny with the magnitude, you will have magnitude distortion. If the phase has got something can produce distortion, that then you will have a phase distortion. So, you have aliasing, magnitude, phase, 3 types of distortions. One of them has been removed. The second one can be removed only if you have if you set the transfer function equal to 1. But this transfer function, setting it equal to this, basically means that it is an all pass function. All pass function. But all pass function, typically the most common all pass functions that we know of are delays, right. Of course, there are filters that have a response which is very close to 1, but they are IIR filters. All pass filters are IIR filters, but now I have a FIR system. Now, the question is, can this FIR system be all pass? Can an FIR system be an all pass but not a delay? Do you understand the question? All pass filters are IIR. The only known case of FIR all pass filters are delays. So, again there is a question mark, can this FIR system actually turn out to be a delay? Again, the answer is yes, but we do not know the steps yet. So, we are following the chronological development. At this point, the question we ask is T of z has to be an all pass function. To the best of our knowledge, only delays are possible, and right now that may not even be an option. So, what about the phase? So, phase response, if phi of omega is of the form a plus b omega, that means it is linear in omega. So, this is the general form of what we refer to as a transfer function with linear phase. A linear phase transfer function is perfectly acceptable to us. Why? Because that tells us that x hat of z is equal to e power minus j omega. If you look at this one, I am just setting a equal to 0 for now, because if a is non-zero is just a complex scale factor. E power j omega b times x of z, right. So, what does this actually indicate in terms of the relationship, assuming b was a integer, then it says that x hat of n is equal to x of n minus b, b is equal to integer. Okay. So, why linear phase? This is the key, because if the output is a delayed version of the input, then you will get linear phase. So, linear phase, you may say no, I want zero phase. No, zero phase means it is a non-causal system, that is not something that we may be able to accept. So, linear phase is the best that we can do in terms of phase distortion. So, to summarize, the key points are that we have 3 types of distortions in a 2-channel filter bank. The first one is aliasing distortion. Okay, that is represented by A of z. Only if and only if A of z is 0, then we can talk about the other one. Then the transfer function becomes T of z. Okay. If A of z equal to 0, if A of z equal to 0, then the transfer function now is T of z, which can have magnitude distortion. If you want to eliminate this, you need to have an all pass function. So, to eliminate, you need to have an all pass function. This basically says make sure T of z somehow is an all pass function, and if you have the phase distortion, that will be eliminated if T of z has got linear phase. Okay. So, the thought process is very systematic. Get rid of the aliasing, whatever transfer function you have, can you make it look like an all pass? Best case, get linear phase. So, if you can show that T of z somehow becomes a delay, then perfect, because it is all pass. It also gives a linear phase, but the question is, it's actually when you design H of z, you design it to be a low pass filter, and then the H1 has to be designed as an all pass filter, as a high pass filter. Now, taking them and constructing this T of z has no control over whether the output will come out to be a delay or not. So, right now this is where we are. So, let us now spend a few minutes trying to analyze what has happened in the 2-channel filter bank. So, the mathematical framework is now in place. We now want to get the insights. So, the pictorial representation, this is usually the best way to get the insights. Okay, and all we are going to invoke here at this point is our ability to downsample a signal, upsample a signal. Okay, so here is a starting point. This takes a little bit of time to draw, but it's worth the effort. Okay, I am going to have 2 filters, H0 and H1, which are approximately of same bandwidth. So, which means that somewhere around pi by 2 they should cross over, but there is no other constraint. If my input signal is Nyquist sampled, then I have a information content all the way from 0 to pi. That is the input signal. Now, I want to look at the first filter, crosses over like this, second filter crosses over there, okay, somewhere around the halfway point. So, the portion of the signal that has been picked up by the low pass filter, that is x naught E of j omega. So, this is H naught, let me use the same colors, red is H naught, blue is H1, green is x, okay, that is the input signal. Okay. So, the first part that we want to pick up is what does the signal x naught look like, x naught e of j omega. So, this is the portion pi. Notice that there is a part of the signal which is captured between in the pass band without any distortion, okay, and then the transition band occurs. So, which means from that point on it will drop. That is the portion of the input that is captured by H naught, filter H naught, and it will have a copy on the other side at 2 pi. So, if you have this as 2 pi, then this is pi, there is a copy of the signal which is mirror image to this. Okay. So, make sure you draw it symmetrically, you can do it better than me. Okay. So, the other one is the portion of the signal that is picked up by H1. Again, it may seem like we are doing something which is fairly basic, but very important that we are able to do it, because this actually gives us the insight that we need to actually design these systems. 3 pi by 2 and 2 pi. Okay. Now, please draw the spectrum of x1. x1 has the following structure: pi, pi by 2, 3 pi by 2. It is a portion of the signal that is picked off by H1. H1 also has got a part that is without any, which basically preserves the input signal because it is equal to 1. Okay. And then there is a transition band. So, in the transition band you will see a sloping part, basically it will, and then the rest of the portion will get, signal will get cut off. So, here again it will be symmetric. Okay. So, I have two portions, the two filters have picked off the respective portions of the signal and have and these are of the order of 2 pi. The total bandwidth that we are talking about is of the order of so that we can actually of the order of pi by so we can do the downsampling by a factor of 2. So, again sufficient condition is that the net bandwidth is 2 pi over m. M is equal to 2. So, the total bandwidth, this is first one has got bandwidth of pi, the second one has got bandwidth of pi. So, I can do the downsampling. Okay. So, first step is the downsampling of x naught. So, x naught downsampled, we labeled it as V naught, V naught e of j omega. Okay. So, please sketch that. V naught e of j omega, first of all says that there is a scale factor of 1/2. So, we have to take that into account. So, basically the signal will go down in terms of spectrum and it will get stretched. It will get stretched all the way to pi. So, it is something of this type. Okay, it is down and then stretched. There is a shifted version of it. This is also present. So, this is the k equal to 0 version of the spectrum, this is k equal to 1. So, basically you have the okay. So, this is the downsampled signal. Downsampled signal has got this overlap, and therefore, there is some aliasing happening at this point. We do not know yet, we need to analyze, but for now this is it. So, can you draw the corresponding this signal downsampled? So, this is V1 e of j omega, this is x1 e of j omega. So, if I downsample it, again I get a scaling factor of half, and there is a stretching, and of course there is a shifted version also. So, very important that we are able to draw it correctly and then be able to draw the scaled version as well. So, if you go ahead and do the careful the drawing of this, basically go through the stretching process and the shifting process, what you would find is that we have the following signals present. There is pi by 2, pi 3 pi by 2, okay, and there is a stretching by a factor of 2 and also the shifted version. So, basically you stretch by a factor of 2 and apply the shifted version, what you find is that you get a version of the signal, scaled version crossing over. Okay. So, basically there is a scale factor of half. Okay. Be very careful how we do that, and basically generate the, if you were to remember how we did the downsampling, what did we do? We first replicated by shifted versions of it and then stretched it. So, if you do the shifted version, you will get a copy of the signal here. So, you will get a copy of the signal which is here for the shifted version, and then you stretch it, that means then that is when you get this portion. Okay. So, be careful when you do the downsampling of a band pass signal, you have to be make sure that you get the correct scaling of the frequencies. This next step is straightforward. From V0 and V1 get the upsampled signals, that is fairly straightforward. Let me just quickly sketch that. So, the spectrum of V0 replicated twice, the scale factor of 1/2 is still present. So, this is pi by 2, pi, 3 pi by 2 and 2 pi. So, the shapes are, again you can probably draw it much better than I can. I will not look for perfection, at least the representation is reasonably close. Okay. So, this portion of it is 1/2 x naught e of j omega. Okay. This is 1/2 x naught of minus e of j omega, the shifted version. Okay. So, basically this is what gets presented when we have the upsampled signal. Onto this I am applying f naught of z. So, f naught of z is a low pass filter, which will have some response of that type. So, the first copy of the signal goes through, that is what we want. It also picks up a portion of x of minus z, that is where the problem occurs. So, the part that we need to eliminate is the portion of the spectrum which is contributed by the following term, x naught e of minus e of j omega, okay, x naught minus e of j omega multiplied by f naught e of j omega. Okay. What is that? Basically it is the intersection of this red filter with the green line, but the shifted version. So, what we get is something of the form, it is around pi by 2, I will get some sort of a bump. Okay. This is the unwanted portion that is coming through the upper branch, and of course, there is a similar copy of the filter on the other side. This is also the unwanted portion. Now, very quickly let us do the other signal just for completeness. I am sure you will be able to do it on your own, but please do try it out on your own as well. This is just for completeness, pi by 2, 3 pi by 2. Basically we said that the shape of the signal is of this type. The shifted version is going to be, okay, that is a shifted sorry, the shifted version is going to be of this type. Okay. Now, to this I have to apply the filter F1, it is a high pass filter. So, the high pass filter will have a response which basically goes from in this direction, and there is a desired portion that is captured. I want to look at what is the undesired part that is captured by the lower branch. The undesired portion that is captured by the lower branch is represented by x1 minus E of j omega multiplied by F1 E of j omega, and that turns out to be also centered around pi by 2, a shape that looks like this, and another one that also is in the frequency content. Okay. Now, why does the signal go to 0 elsewhere? On one side, because the filter itself goes to 0. On the other side also the unwanted portion of the spectrum. So, basically the unwanted portion is what we are looking at. So, that this is the wanted portion. So, this is the, I will put a tick mark for the wanted portion, this is the wanted portion, this is the unwanted part, this is the unwanted part. So, the unwanted part filtered is what is here. Now, notice that when we achieve aliasing cancellation, what is actually happening? These two unwanted portions are cancelling each other. Okay. Now, what is passing through from the upper branch? What is passing through is the following signal, is a signal that is of this form, and something which is, okay, that is what is passing through from the upper branch. From the lower branch, the signal passing through is something that looks like this, and the combination of these two is the resultant reconstructed signal. So, it has all of the frequency components, but the combination of these two may have magnitude distortion, we do not know, may have phase distortion, again that is the part that we would have to deal with. Now, we have to take the next step. So, at this point we look at the problem and we say, okay, what are the options that are left to us? Okay. Can I do something with the filter design H0 and H1, because obviously I am trying to get the T of Z to become a delay. So, yes, I would like to explore the option of the delay, the T of Z. So, when you start going in that direction, I have to solve a magnitude problem, I have to solve a phase problem, distortion. So, to eliminate one of them, I will try to see whether I can restrain myself to linear phase filters. H of Z, H0 of Z must be a linear phase filter. If I say that, if my resultant comes out to be linear phase, the T of Z turns out to be linear phase, then I am in good shape. The answer is, it may be sort of obvious that that is the right way to go, because if H0 and H1 are constrained to be linear phase, the product of them will be linear phase, and therefore I am kind of moving in the right direction. So, I will explore that option as one thing. The other option that we want to explore is, hey, we are multirate signal processing. Okay, we have done polyphase components. So, well, can I do something in the polyphase component domain? Split H0 of Z into polyphase components, into two polyphase components, and see if there is a better insight. That is possible too, right? We can say that maybe rather than dealing with the filters, since anyway downsampling is going to happen, I may want to look at it in the polyphase domain. No, that is a second option. So, we will look at it both from the polyphase approach and from the linear phase approach. So, quickly brush up your, there are 4 types of linear phase filters. We will be looking at type 2 linear phase filters, and we will justify why. So, in case you have not forgotten them, just look at what type 2 linear phase looks like. The other option is, can you redraw this figure, the 2 channel filter bank case? Can you redraw this in terms of the polyphase components with the following constraint? Okay. So, this is the task for you to do. The task is the 2 channel maximally decimated filter bank, okay. You do polyphase components with the following constraint, do type 1 for the analysis filters, analysis filter bank, you do type 2 for the synthesis filter bank, and then do apply the noble identities, because you will it will lend itself to applying the noble identities and obtain the simplified structure, resultant structure. So, if you can come prepared to sort of with the resultant structure, one step the polyphase component part we can address, resultant structure. The other one is come with the expression for type 2 linear phase filters. We plug in, we see what is the condition that we get. So, the answer, the key question is how do we solve, do either of these options give us a solution where we can satisfy x hat of z is equal to c times z minus n naught x of z, or in other words x hat of n equal to c times x of n minus n naught. Why is this? Because this is what we refer to as perfect reconstruction. You are reconstructing it to within a scale factor and a delay, perfect reconstruction. So, ideally we would like to achieve perfect reconstruction when there is no signal compression and other things, just the synthesis filters, and so this is our ultimate goal. No aliasing, T e of j omega equal to c times e power minus j omega n naught, that is it. Scale factor, linear phase, and then we achieve the result that we are looking for. Okay. So, we stop here, but please do try the polyphase implementation as well as a review of the type 2 linear phase filters. That will be very helpful for us in next class. Type 2 linear phase in Oppenheim and Schaefer, it is present. The portion that we have done today is in Vaidyanathan's book, P.P. Vaidyanathan's book, chapter 5. Again, definitely and encourage you to read, because that will sort of set the stage for everything that we are going to discuss in the next class. Thank you.